Most devices, static and dynamic behavior. So we will try to look at the static behavior, DC response, and logic level and noise margin. And the dynamic response like transient response and delay estimation in detail. So there are several the exercise. Let's say if the width of a transistor increases, the current will increase or decrease. It will increase, right? So we can write down I equal in saturation half mu n COX W over L VGS minus VTH square in saturation, for example. Or in triode region, we can write down in triode, what is triode? In triode, I equal ID equal mu n COX W over L VGS minus VTH VDS minus VDS half square, right? You can double check the equation with the VDS equal to VGS minus VTH. That will give you to saturation equation. As you can see, W increase, that will increase. The current will increase. The length of transistor increase, then current will decrease. If the supply voltage of the chip increase, then current will what? The VGS become VDD. We plugged in for the logic either 0 or VDD, right? So VGS, if the VGS become VDD, then current will increase, right? So supply increase, the current increase. If the width of a transistor increase, the gate capacitance will increase, right? The area, gate area is increased. The length of a transistor increase, its gate capacitance also increase. If the supply voltage of a chip increases, the gate capacitance of each transistor will what will happen? Supply voltage of a chip increases, gate capacitance of so gate capacitance between is formed by between what the physical dimension, right? So it if the supply in digital, it does not changes, right? Okay, this is the final result, and then you can double check the answer. Okay, the load line analysis for here. Typically we can start with the resistive load like this with the MOS to inverter to implement the inverter. So input and output. So we can write down the truth table, input and output. If we apply 0 to the input, the output will be VDD because the MOS is totally off. But when we apply the VDD onto the input, what would be the output voltage? Actually, when you think about when we make this MOS turn on, the output will be driven to low voltage because of the switch is driving. Switch resistance is very small, but eventually the output never goes to 0. There should be some non-zero value because there's always finite current flows through the resistance, right? If there is a voltage drop there. Then now the question is, what would be the output actual voltage?
To calculate the output voltage, we have to know the operating point region of the MOS. We assume that V out is less than VDD minus VTH. This is overdrive voltage of the MOS. Definitely, let's say for example, VDD 1 volt and threshold voltage 1.3 volt. That's gonna be 0.7 volt for the overdrive voltage, which is very large. So output definitely less than this overdrive voltage. So we can make sure that the transistor in triode region, right? So we can write down the equation ID equal to UN COX WOL VDD minus VTH V out. V out is now the VDS of the transistor, right? So minus half V out square, right? This is the triode equation. This current must be same as the current through the resistor. That would be the current would be voltage drop across the resistance, that is VDD minus V out, right? So we can find out the V out by relating those two equations. Those two equations are same, but in triode region, V out is very small, so we can ignore this square term. V out is less than 1, so each square would be close to 0. So we can make it simplify to find out the V out here, right? You can find out V out using this equation, right? So the inverter with so I told you that we always deal with ID equal mu n COX WOL something half VGS minus VTH square in saturation. So those parameter mu n COX WOL quite difficult to calculate or extract from the device model file. But one simple way to know this relationship is that first we know that we, for example, apply the, let's say, known current, let's say 1 milliamp for the known device size, for example, let's say 10 micron over 1 micrometer device. So during the design process, let's say we flow the current, known current through the device, and we can look at what is the voltage between gate and source for this amount of current, and what would be the threshold voltage and what is the overdrive voltage of through this arrangement. So if you know that, you can easily know that the threshold voltage and overdrive voltage by looking at the DC response, right? So from there, we know that current is 1 milliamp and half mu n COX, and VGS and overdrive voltage here, overdrive voltage in here, right? This relationship is there. So if we assume that device follows the device model, scale law model, if we know that current and overdrive voltage, then we know that those numbers, UNCOX, WOL, that would be 1 milliamp over V overdrive square, right? This number. So all these number are factored into this calculation. So actually, when you design a circuit or find a small signal parameter like a GM, we know that GM, the transconductance, has three different equations. That is, first one is 2ID over V overdrive. Second one is what? Mu n cox W over L V overdrive voltage. The other one is square root 2 mu n cox W over L V overdrive. Would you like this? Alright. So those two equations require mu n cox W over L information, but the first equation doesn't require, right, this number, because once we know the current and overdrive voltage of the transistor, then we can easily derive that mu n cox W.
The second type of the upload is PMOS. So let's say we have a PFAT with a constant current load like this, some bias voltage applied, MFAT. So V in, V out, we know that V in 0, then V out will be VDD because this is a current source, constant current source. Alright, we have VDD. If the PMOS current source is IP, then the input, the pull down current must be greater than IN. IN must be greater than IP so that output can be pulled down, right? So close to 0. But in this case here, still we have a constant current, pull down current, right? Initially, let's say initially IN will be greater than IP, but once the output close to the 0, then MMOS will get into triode region, and then the output current IN will collapse until IP and IN equalizes, right? So this voltage V out is the VDS of the MMOS. The VDS becomes the output of the above the logic gate. This output will never be 0 because there's a constant current IP from the pull up PMOS current source. So when the IP and IN equal, at that point IP equal IN, the output final voltage will be determined, right? So it has also non-zero steady current, and it gets the steeper transfer curve, meaning it will have a input voltage versus output. It will have something like this kind of a relationship. Steep V out will be steep voltage transition. The last most important option is to use PMOS complementary switch, meaning so we apply the complementary input. So we have a bubble, so it is inverted output, inverted input. So in this case, we have a 0 steady current because only one of those PMOS or MMOS, only one of those will be on. So it has a large noise margin even with the large noise on the supply or noise on the input. The output will be properly generate the logic function. For example, let's say if the supply, assuming supply is clean VDD and ground, clean ground, input is noisy, with this buffering, the output will be properly generated, so from the clean supply and ground. So we will go through the noise margin definition later, but for now we just remember the inverter with PMOS complementary switch will have a zero static current. That's pretty much the most important feature that in modern technology utilize this kind of a complementary logic style. Let's take a look at the complementary input inverter more in detail. So DC response we will look at for V out versus V in, right? V in, V out versus V in. So when V in is 0, the output will stay at VDD, right? So if V in is VDD, then the output will be at the 0. So we have a two operating point, let's say, and the in between. So when the input is in, let's say, half VDD, then somewhere in so pull up and pull down current, matches, so the output will be somewhere in between VDD and ground. So this is the point, the IDSN equal IDSP, PMOS current and MOS current equal with this relationship. So if you to continuously monitor and then extend the transfer curve, eventually it will look like this. So we can find this curve by solving the equation, but the graphical solution gives more insight rather than the solving mathematical triode saturation equation. So we'll go through. So transistor operating region, we know that cutoff linear saturation. So we will look at each device's operating region for input versus output versus input, right? In the next slide, let's take a look at for each device's operating region. Following this all, so we know that V in, V out. So in each point, what would be the operating region of each transistor, right? Let's look at the MOS operating region. So for cutoff, VGS of the MOS must be less than VTH and GS and linear region for GS must be greater than VTN, and DS must be less than overdrive voltage VDD minus VTH and TN, like this. VGS here, saturation region, again VT greater than VTH, VDS must be VDD minus VTN, and so here TN, VGS, and here VGS must be is the we haven't assigned the VDD yet, so we just keep the VGSN here, VGSN there. Since the VGSN equal to V in and VDSN is V out, we can replace that equation. So V in less than VTH cutoff, V in greater than VTH, and the output is less than overdrive voltage, then linear output is greater than overdrive voltage, then saturation region. Alright. So here overdrive voltage V in minus VTN, right? So V in, so V overdrive, right? So this thing, PMOS operation. PMOS is always confusing for most of the students because it's gate voltage relationship and threshold voltage is quite different. I mean, threshold voltage is negative voltage and VGS is kind of some different convention there. So we know that source, gate, and drain, to turn on, we must apply VSG greater than threshold voltage of a PMOS and absolute, because when I put the absolute there, because of threshold voltage defined as a negative voltage, because let's say if you take that negative, the absolute value there, then it become minus VTHP, so that it becomes a positive number. So VSG, if you write down, then VGS, then change the equality, then the what, plus VTHP, something like that. So this is something that you want to make it on condition. In this case, the cutoff case, we have to apply that VGS greater than VTHP, right? According to this convention. And also, if you make it linear, then make it on, then VGSP must be less than VTHP. Here, VTH saturation, also VTHP. For the overdrive voltage, again, we can define the overdrive voltage. VSD must be greater than VSG minus VTHP absolute, right? For saturation, in saturation, right? The voltage drop between source and drain must be greater than this overdrive voltage, because the PMOS as voltage current is flow from source to drain. We know that voltage of the source is greater than drain voltage, right? So current flow from the higher voltage to lower voltage. So this condition you can rewrite again, VSD greater than VSG plus VTHP, because this is negative threshold voltage there. So this relationship, we can change VDS and then take the minus. So this one, change the direction, and so change the direction here, minus VTHP, like that. So this is something in saturation requirement. So VDS must be less than VGS minus VTHP, or this one greater than VGS minus VTHP. So it's a very complicated mathematical derivation for PMOS. But what I prefer to drive is that this kind of convention, right? This convention and this convention is much more insightful for analog circuit designer and consistent with the MOS operation. Okay, so this is the final answer. Again, this is the same as what I derived. Okay, now we replace the VGS with the actual input Vin. So VGS, this is source and gate. So VGS is the V in minus VDD, right? So here, so V out, we have a source and drain. So VDS is V out minus VDD. So we know that threshold voltage of the PMOS is less than 0. With this relationship, we can plug in those things to the table. So finally, we get those massive, complicated equation of those. One thing that note is that this is, although it looks like complicated, we can visualize its output and input relationship like this. So on the right hand side is a conventional NMOS device characteristic. On the left hand side is the PMOS device characteristic. So on the y-axis, positive axis, we are plotting IDSN, and for the minus side, the minus IDS is plotted. So all these are quite initial. For the first look, you might be very confused why this kind of a plot showing in here. But what you have to remember is that this behavior is very similar to that of the NMOS device, right? So this is the odd symmetry, right? So typically PMOS we draw wider because the mobility difference. So we assume that the mu n, in this case mu n over mu p approximately 2, we assume that. So we draw like 2x larger W in PMOS than that in the NMOS. Now we move the plot with the V out versus the V in, right? For the NMOS device like this, PMOS are drawn like that. So we again took the absolute current. So for the different input, we have so we can get the different output current level. So what the plot shown here is that, for example, if the V in is low, like in this curve, let's say the NMOS will have this kind of curve relationship. If NMOS is like this, then PMOS curve will like this curve, right? I'm sorry, this is V in. PMOS will have this curve. So this first curve and the second curve will find at this point, this is actually what the output will be. So we have two different equations, and then satisfying those two equations is only here. For example, for V in 4, we have like this line curve for the NMOS. For the V in 4, for the PMOS is the this curve, right? What is this? Where is 3? V in 0, 1, 2, 3, 4. 4 is like the 0, almost 0. So output will be here, around 0. What about V? Where is it? So some looks like the missing some here. So let's try to V in 3 here. V in 3 curve here. This curve is the PMOS curve, right? And this is NMOS curve. It collides with this point. This is actually the solution for the output. So we can find the cross section of the two equations and then determine the output voltage, right? You can visualize in your brain and how the output current equation changes for each input level. So we can find the solution by looking at where the crossing point happened. And so again, so for a given input, we can plot the IDS for the PMOS and NMOS versus Vout. So we can find the Vout. So by looking at the Vout must be where currents are equal for the pull up and pull down. We will look at the one by. For example, if the Vin is 0 for this structure, the 0, Vin is 0, NMOS will be off, no current, and PMOS will be on in, right? So output will be VDD. So PMOS will have this kind of a current relationship because output the VDD, right? V out. So VSD is VDD minus V out. So if you reduce the VSD, then I'm sorry. If you so here VSD of the PMOS VSD is VDD minus V out. So if the V out level close to VDD, then VSD is 0, so no current for the PMOS. If you reduce the V out, then VSD larger, so it has more current like this, right? That's what it is. Now if we increase the input voltage, then what happened? So the NMOS is not yet turned on, but VSG actually reduced because input voltage level goes up, so current will go down like this. So overall curve relationship like that, but yet the NMOS current doesn't flow because this level is not greater than VTH of the NMOS. Now once the past the input level greater than NMOS transistors, the VTH, then NMOS now start flowing the current. So we know the relationship between V out versus and the current level, and PMOS will have the like that. So only crossing point is here. This is what actually output electrically satisfying the KCL and KVL. This is the only condition that will satisfy the KCL and KVL. So this is what the output level of the inverter for this input 0.4 VDD. If you further increase the input level, then NMOS will flow more current. It will have this kind of curve relationship, and PMOS will reduce the current. So those two equations, this point is the satisfying output level, so output becomes low. And finally, if the input close to 0.8, then PMOS turns off and only NMOS turn off, but the only solution is here, and output will be near 0. Again, if the Vin is VDD, the totally output becomes 0. So now we found that how we find the crossing point of the two equations for different input level. Now we will draw the output level versus the input voltage in the next slide. Here again, so as we increase the input level, output voltage will follow this red curve. But you can notice that in each section, like section A, B, C, D, E, each PMOS and NMOS will have a different operating point, operating region. So we will determine how these points are related with the NMOS and PMOS operating regions.